everyone. We are going to start chapter 19, which is about chemical thermodynamics. This is going to be kind of more of a bridge focusing on kind of more in-depth things from chapter 5, which was just thermochemistry. So we kind of talked about some ideas in thermochemistry about enthalpy, and we talked about entropy. We also talked about like Q equals MCAT, and the first law of thermodynamics we hit also in chapter 5. We'll cover that again in this chapter, but we're really going to delve into the other two laws of thermodynamics, and as well as, I think, taking a step further, really taking a step further entropy, but then also kind of talking a little bit more about enthalpy in the process as well. So first steps first. Let's talk about the first law of thermodynamics, and that was from chapter 5. And ultimately, we know that the first law of thermodynamics states that energy cannot be created nor destroyed. So another way of saying that is that energy is conserved if we're talking about a system. So the total energy of the universe is constant. So if I'm thinking about the universe as being a system, then I know that the total energy of the universe must remain constant. I'm not creating energy, I'm not destroying energy, but that's not saying that we can't transfer energy. It's not saying that we can't convert like potential energy into kinetic energy, because that happens. It's not a creation or a destruction of energy, it's simply just a new way that the energy is now presented. So energy can be converted or transferred, whether it's from the system or to the surroundings, or from surroundings to the system. So the mathematical law of the first law of thermodynamics, what I want you to write down is delta E is equal to Q plus W. Delta E equals Q plus W. Let me pull up the Promethean board, guys, too. So change in energy is equal to Q plus W. This is the mathematical statement, or the mathematical law of the first law of thermodynamics, meaning that my change in, and specifically I want to talk about this E here, change in energy is equal to Q, we know it's just heat, and W is representing work. So my change in energy is simply just the sum of the heat that's either absorbed or released by the system, in addition to the work that's either done on the system or the work that's done by the system. So remember that if we're talking about Q, if we're talking about heat, if Q is positive, if Q is greater than 0, then that means the system is going to absorb a certain amount of heat. So if Q is positive, then that means we've absorbed. System absorbs heat. But if Q is negative, then that means that the system is going to release heat. Okay, same thing let's talk about with W, with work. So if the system, or let's say, what happens if W is greater than 0? If work is a positive entity. So if work is positive, then that means that the surroundings are doing work on the system. So if work is positive, surroundings do work on the system. So that would be like, I'm trying to think if I have anything really good here. Okay, so I have my bottle of lotion here, and if I'm the surroundings and my system is a bottle of lotion, I can push this valve down and do work on this system to release some of that lotion out. So ultimately, I can have I'm applying energy to that system. So surroundings are doing work on the system. Work is considered to be a positive entity. If the system does work on the surroundings, then that's going to give us a negative value, or work is going to be less than 0 in those cases. Okay, so that's kind of a throwback here for chapter 5. So let's go back. Okay, so spontaneous processes. A spontaneous process are those that can proceed without any outside intervention. So a spontaneous process is really just something that can occur in only one direction. So I want you to think of a spontaneous process as only being able to occur in one direction. So if this were a reaction, if we were writing a chemical reaction for this, the arrow's only, I'm only going to have one arrow. I can't go back. It's not reversible. Which is kind of different, kind of a shift from thinking about our equilibrium reactions that we've been doing here for a while. But I could say that the reverse process of that is something that I would call a non-spontaneous reaction. So let's say we know that energy is conserved. And we are always going to know that. And experience tells us that certain processes will always occur. Certain processes are always, always, always going to occur. When I place water in the freezer, let's say I just take an ice cube tray, fill that ice cube tray up, and I place that ice cube tray in the freezer. I know that that water is going to turn into ice. I know that process is going to happen. Same thing, I know that if I touch a really hot object, if I accidentally place my hand on the stove if I'm cooking, I also know then that that heat is going to be transferred to my hand. But non-spontaneous processes would be if I'm thinking about the reverse of those reactions. So if I place my ice cube tray of water and I just set it out on the counter, I shouldn't think that spontaneously that water is just going to turn into, if it's still at room temperature, it's not just going to randomly turn into ice. So spontaneous processes are things that really are just kind of logical to us. We know that they occur, and they happen without really any outside intervention. They're happening on their own. I don't need to apply really any extra energy to make them happen. They're proceeding on their own. Couple different, if we're looking kind of here, so I have gas at 1 atmosphere here in this part A, and they're connected, and I have the stopcock here is closed, and then in part B, I have just an evacuated flask, so there's 0 atmospheres on this side. Ultimately, we know that if we think about it logically, spontaneously, if I open the stopcock here, some of the particles that are here in A are going to move over here into part B. And if I'm thinking about, it should reach some type of equilibrium. So this process is going to happen where ultimately I'm going to have an even distribution of particles between A and B, because that's just a spontaneous reaction. A non-spontaneous reaction would be if I had some of these molecules move into part B, and then all of a sudden, all by themselves, those particles left flask B and moved all the way back into A. Particles just won't do this by themselves. That's non-spontaneous. So that would be considered a non-spontaneous process. So a spontaneous process is one that will proceed on its own, no outside intervention. If I want the particles to move from flask B back into flask A, I'm going to have to use some type of outside intervention, whether it be heat, whether it be doing some amount of work on those particles in that flask. Something is going to have to create those particles to move from here to here. So that would be a non-spontaneous process. Okay, so again, processes that are spontaneous are in one direction. Non-spontaneous processes are just a process that's in the reverse direction. So I have 2 eggs. If I drop the eggs, they fall, they're going to break. That's a spontaneous process. It's going to happen without outside intervention. Gravity sucks. That's what happens. Eggs drop. Now, all scrambled eggs here on the bottom. Non-spontaneous process would be Could I ever get those eggs, get the shells back together the way that they were before I dropped them? No, I'm never going to be able to do that. That's a non-spontaneous process. And I'm at least not going to be able to do that without some type of outside intervention helping form those eggs back together to make them go up here to where we had them originally. So processes that are spontaneous at one temperature may also be non-spontaneous at other temperatures. So above 0 degrees Celsius, it's spontaneous for ice to melt. But below 0 degrees Celsius, the reverse process is actually spontaneous. So temperature is something that we also need to take into consideration if we're thinking about whether or not a process is going to be spontaneous or whether it will be non-spontaneous. Okay, so let's predict whether each process is spontaneous or if it's spontaneous in the reverse direction. If I ever ask you, or if you were asked on the AP test, is a reaction spontaneous in the reverse direction? Ultimately, they're just asking you, is it a non-spontaneous process? Or is a reaction in equilibrium? We could possibly have a question that asks us that. So, first one, water at 40 degrees Celsius gets hotter when a piece of metal heated to 150 degrees Celsius is added. So water at 40 degrees Celsius gets hotter. So I just have like a beaker of water right now, and I took the temperature of that water, and it says it's 40 degrees. Now I'm going to add a piece of metal that's 150 degrees Celsius to that 40 degrees Celsius water. I want to know, is there going to be a spontaneous process or a non-spontaneous process by saying that the water is going to get hotter when I add this piece of metal that's 150 degrees Celsius? This is going to be a spontaneous process because we know heat is going to transfer from a hotter object to a cooler object. The heat of the metal is at 150 degrees Celsius. That metal has a lot more energy than this water does. So because the metal has more energy, it's going to transfer some of its energy into that 40 degrees Celsius water, raising then the temperature of the water. So yes, the water will get hotter when a piece of metal that's hotter than the temperature of the water is added. So this first one is going to be a spontaneous process. The second one, it says water at room temperature will decompose into hydrogen and oxygen gas. Okay, so we are completely made, we're mostly made of water. Guys like 80%, girls like 65 to 70% made of water. And that would be like saying, I just have a beaker of water that's sitting out on our lab station, and all of a sudden this water is just at room temperature going to decompose into hydrogen and oxygen gas. Does that happen? Is that logical? No, it's not. But is the reverse reaction spontaneous? Yes, it is. Hydrogen and oxygen gas will spontaneously form, they'll synthesize to make water. But the reverse reaction does not happen on its own. I have to force this water to break down into hydrogen and oxygen gas. So I would say that this is spontaneous in the reverse direction. So ultimately, I would call this a non-spontaneous process, or I could say it's going to be spontaneous if we're talking about the reverse reaction. This next one says benzene vapor at a pressure of 1 atmosphere condenses to liquid benzene at the normal boiling point of benzene, which is 80.1 degrees Celsius. So ultimately, this is just saying we're at the boiling point here for benzene. And if we're at the boiling point, remember we said that's a dynamic equilibrium. And so ultimately I can just say this is a process that's in equilibrium. Okay, so let's also continue our thought pattern about reversible processes, and then let's also talk about something called an irreversible process. So to understand why certain processes are spontaneous, we must first consider the ways in which the state of a system can change. A key to understanding spontaneity is understanding the differences in the paths between these states. Heat and work, we talked about in chapter 5. We talked about before that heat and work are called state functions. So we talked about that heat and a state function is something that will depend on the path that's taken. State function depends on path taken. heat and work are not state functions. They do not depend on the path that's taken. So in chapter 5, remember, we talked about state functions. State functions are something that heat and work are not state functions. And ultimately, in 1824, there was a man named Carnot, Carnot. He worked on something where he tried to make a steam engine, and he thought he could make the perfect steam engine, and he thought that he could work with the efficiency. He said, I could get the steam engine's ability to convert heat into work, and I could get that to be 100% efficient. But ultimately, he did so many tests and found out that that wasn't true. But he considered what an ideal engine would be, and he observed that it's impossible to convert the energy completely into doing work, because there's always going to be a significant amount of heat that's lost to surroundings in many, many processes. So what I want you to take from that, what I just said, is that ultimately we usually lose quite a bit of heat to the surroundings in most of our reactions. So we're never going to have an ideal system. Nothing will ever be 100% efficient. So a reversible process, let's now talk about a reversible process. A reversible process is a specific way in which a system will change its state. So a reversible process is a specific way in which a system will change its state. Heat can flow reversibly between a system and its surroundings. And that's just something that we know. Water, liquid water, can easily move and be evaporated into gaseous form, because I can see that more apparent if I just leave a glass of water out. Ultimately, that water level is going to decrease. So same thing as if temperature decreases and I can have gaseous water or water vapor that's in the air start to condense to form back into a liquid. So a lot of times we see heat flowing reversibly from systems into surroundings. So we can have reversible processes if we think about just normal everyday applications like water. But there's something that has to be said with temperature. So a lot of times with temperature, if we increase the temperature of the system,